Hello everybody, this is again Mikhail Pogosyan. This is our probability lecture number 22. Today we're going to talk about continuous random variables. Now, last time we were considering another type of random variables, discrete random variables, and today our talk will be about continuous random variables. We will give the general theory of continuous random variables, and later in our next lectures we will consider some different particular cases of continuous random variables. From the last lecture we have learned that a random variable x is discrete if the range of x, that is the set of all possible values of x, is either finite or countably infinite. So we can enumerate all possible values of x by natural numbers or its subset. If we have a discrete random variable x, then we can describe it through probability mass function, through its PMF. So what is a PMF? It is a table of this form or a function as a wish. What this table represents, here we have the values of our x, and here we have probabilities. So the probability that x will take the value x1 is p1, the probability that x will take the value x2 is p2, etc. Now, having that PMF, we can calculate probabilities like this. So probability that x is in some subset A can be calculated by just adding all probabilities pk over the indices k such that xk is in A. And we have learned last time that the CDF of our discrete random variable is a piecewise constant function, or which is the same as step function. Now let's talk about continuous random variables. There are many random variables that are not discrete. For example, we can consider a lifetime of a light bulb as a random variable, or the height of a randomly chosen person, or the age, not rounded age of a person, randomly chosen person, or the waiting time for a metro train, say. And all these examples are not taking discrete values and are not discrete random variables. So the idea of continuous random variable is not so hard, but the definition of continuous random variable, unlike discrete case, cannot be given by just describing this kind of probabilities. And this is because all these probabilities for a continuous random variable x will be 0 for any real number small x. So we will not talk about probabilities of this event, the event that x is taking a particular value small x, but we will rather talk about combined probabilities, probability that x is between some real numbers a and b, or maybe about probabilities that x is in some subset of R. The idea of defining probabilities for continuous random variable is similar to defining the mass of a physical body. So we cannot define the mass of a body by using the masses of points, because each point has 0 mass. And rather, we are defining the mass of a body, of some part of a body, by just invoking our knowledge from calculus, by just invoking integration. To calculate the mass of some part of body, we are integrating the density over that part. So in the analogy, similarly, we will define the probability of x, continuous random variable, being between a and b by just integrating the probability density function. So we will define what is the density, probability density function, and we will calculate this probability by just integrating that function over a and b. But before that, one lyrical zero minor minion. So this is Zeno's paradox. We are one of the Zeno's paradoxes. In fact, say we are considering an arrow in the flight. At any time instant, the arrow is not moving, is motionless. So you can think about that as recording the flight and then considering just one frame at a time of your movie at a time. You can have a still image, you can have a motionless arrow. Then how can it move at all? In fact, it turns that the motion is consists of infinitely many motionless instants. Okay, so let's go back to our continuous random variables and define what the continuous random variable is. Assume x is a random variable and capital F is its CDF. So we say that random variable x is absolutely continuous or just continuous if there exists an integrable non-negative function f defined on real line and taking real values such that the CDF at the point x is the integral from minus infinity to x of that function small f for any x. And this small f is called the probability density function PDF of random variable x. So if small f is the PDF of continuous random variable x, then the CDF can be obtained by integrating that PDF from minus infinity to x for any x from real line. Sometimes we will write in the index that random variable x to show that this PDF is the PDF of that random variable x. And a remark from real analysis and calculus 2, the remark is that if f is integrable function, then this function, the integral as a function of upper limit, is a continuous function. So if we have a continuous random variable, then its CDF will be continuous at every point x. Now, let's talk about relationship between the PDF and CDF for continuous random variable. Assume that capital F is the CDF and small f is the PDF of our random variable x. Then by definition, we have that CDF can be calculated by just integrating the PDF from minus infinity to x for any x. By the way, I am not writing f of x dx, not to confuse with this upper limit x. And using the real analysis or calculus tools or theorems, we know that if we will calculate the derivative of this thing, then we will get, say, let me write it here, the integral from minus infinity to x f of t dt. If I will calculate the derivative of this function as a function of x, then I will get just the value of integrand at the point x at this upper limit. So using that, we will have that the derivative of CDF will be the PDF. So having PDF, we can calculate the CDF by integrating from minus infinity to x, and having CDF, we can calculate the PDF by differentiating that CDF. And this works for any point where small f is continuous. Now, let's talk about the characterization of probability density functions of PDFs. So, we have learned last time that CDF has can be characterized by several properties. So it is a function between it is taking values between 0 and 1. CDF, I'm talking about CDF. It is taking values between 0 and 1. It is increasing. It tends to 0 at minus infinity, and it takes to 1 at plus infinity, and it is right continuous at every point. So we want to give a characterization for a PDF of a continuous random variable. So it turns out that if x is a continuous random variable with PDF small f, then f is non-negative for any x, and the integral from minus infinity to plus infinity, so integral over the whole real line of f is 1. And a nice thing is that these properties are sufficient to have a PDF for some random variable x. So if we have a function f which is integrable and satisfies these two properties, then there exists a probability space, and there exists a random variable x such that our function f is the PDF of that random variable. So if we will check that small f satisfies this property, then we have random variable having that f as its PDF. So the proof of this can be reduced to the proof for CDF just by considering, let me erase this from the last slide, just by considering this function minus infinity to x f of t dt. Assume we have a function that satisfies this property and its integral is 1 over the whole real line. Then first thing is that f will be continuous at every point because it is an upper limit integral from some integrable function, and this is from real analysis. Another thing is that f at plus infinity will be, if I will plug here plus infinity by this property, it will be 1, and f at minus infinity, if x will tend to minus infinity, this will tend to 0, so this will be 0. Another nice thing is because we have that the derivative of f, capital F, is small f, then and small f is a non-negative, then capital F will be an increasing function. Well, of course, this is not completely correct. We need to take into account that this holds for continuous, for the points where small f is continuous. At some points, this will not hold, and we need to take care of that point. And finally, because f is an increasing function and f tends to 0 at minus infinity and tends to 1 at plus infinity, f will be between 0 and 1. So that capital F will satisfy all properties of CDF. So there is a random variable behind that CDF. That is, there is a random variable such that small f is its PDF. Sorry. Some notes about PDFs, about continuous random variables. So if x is a continuous random variable, that doesn't mean that its PDF, small f, is continuous. So the only properties that f will satisfy, will need to satisfy, is that f needs to be non-negative integrable function with integral 1 over r. F can be continuous at every point, but also f can be discontinuous at some points. And if x0 is a discontinuity point of small f, then it is not necessary that f is right continuous at x0. It can happen that f is left continuous at that point, or f is discontinuous from both sides. And in fact, the value of f at finitely many or even countably many number of points is not important. We'll talk about this later, and I will give an example. And another note is that if x is a continuous random variable, then its CDF is uniquely determined, but PDF is not uniquely determined. We can change the value of our PDF small f at some points, finitely many points or countably many points, and this new function will still be a PDF of our random variable x. Now one example. So this is a graph of some function f, small f. This function is non-negative. It is 0 up to the point -2, and starting from point 2, it takes the value as 0.2 between -2 and 1, and if x is between 1 and 2, it takes the value 0.4. Okay, so f is non-negative. The integral of f over -infinity to infinity is 1, because by integrating this function over -infinity to +infinity, we are calculating the area under that function over the whole real line. And the area will be 1, because we need to calculate these arrays. And here I will have 0, here we will have 0. The area of this part of this rectangle is height is 0.2, width is 3, so 3 times 0.2, that will be 0.6 area here, and 1 times, this is 1, the length is, the width is 1, and the height is 0.4, so we will have 0.4 as the area, so in the sum we will have 1. So the integral of our function f over the real line will be 1. So f is a PDF of some function, a random variable, of some random variable. If I will, I'm not specifying what are the values at -2. Maybe this is the value of our function, and in that case I will have something like this. I need to draw something like that. Or maybe this is the value of our function f, and here I need to make something like this. So at -2 the value is 0.2 for our PDF, or maybe even it can happen that the value of our function f is 0.3, and we have something like this. This is not important, because we will calculate probabilities by just integrating. So if I'm integrating, and say if I'm integrating in this region, and I'm changing the value of my function at one point, that is not changing the value of my integral. So from the point of view of integrals, this function, or if I will change to that, this function are the same. Okay. So let's move forward. Another note about continuous random variables. If x is a continuous random variable, then its CDF, capital F, is a continuous function over R, because it is an integral from -infinity to x of some integrable function. But the inverse is not true in general. If we have a CDF which is continuous everywhere, that doesn't mean that random variable behind that CDF is continuous. But this is an advanced topic and we will skip that. You can think about that, you can read in advanced probability courses and textbooks. And another note is, in all our examples we will give later, we will consider PDFs either will be equal to 0 outside of some interval, like the previous case. We will have some functions as PDFs like this, so 0 up to this point, then some function, then 0 starting from this point, or we will have PDFs that tend to 0 when x is tending to plus infinity and minus infinity. So we will consider PDFs like this, and our PDFs will tend to 0 at both plus infinity and minus infinity. But the note is, the remark is, in general case this is not true. Although we will give only that kind of examples. If f is a PDF of some random variable, then not necessarily f tends to 0 at plus infinity or minus infinity. And think about giving some examples of functions of that type. So you need to bring just an example of a function which is non-negative, and the integral of that function is 1, and that is not tending to 0 at plus infinity or minus infinity. And the next note is about inequality for CDF. So every CDF satisfies this inequality. It is between 0 and 1 for any x. Is it true for PDF? Is it the case that PDF f is between 0 and 1 for any x? The answer is no. You can think about that. You can give an example of that kind of function f. Later we will give an example of that type. Okay, so now we want to give the geometric interpretation of PDF and calculation of probabilities by using PDFs. So by definition of a continuous random variable, the CDF of that random variable is written as integral from minus infinity to x of a PDF of that random variable for any x. And by definition of CDF itself, the CDF is the probability that that random variable is taking values less or equal than x. Now, from real analysis and calculus, we know that the integral of f from minus infinity to x is the area under the curve of that PDF over the interval minus infinity to x. So from this relation we will get that this probability, the probability that capital X, random variable x, is less or equal than small x, is the area of the region under the curve of PDF over the interval minus infinity to x. So graphically, what we have here, so this is the graph of our PDF. So this is the PDF graph. I have it here, PDF graph of some random variable. The integral of this function over the real line is 1. So the shaded area, the shaded region area, is the probability that x is taking values less or equal than 1. It is the value of our CDF at 1. Say, if I want to calculate what is the probability that x is taking values in this region. So from minus infinity to 1.5. To calculate that probability, I need to calculate the area left to that point and under the graph of our CDF. sorry, PDF. This is the PDF graph. Okay. And an important fact is if this is the graph of a PDF of some continuous random variable, then the area under that graph will be 1, because the integral of a PDF from -infinity to infinity needs to be 1. Now, our main point with random variables was to be able to calculate probabilities concerning that x. Probability that x will be some in some interval AB, or x will be in some set capital A. Now we have learned that the probability that x is less or equal than small x is this integral. And we know from the CDF topic that this probability can be written as the difference between the values of CDF. So f of b minus f of a. F of b is this integral at the point b, so we are substituting here at b. F of a is this integral up to the point a, so integral from -infinity to a of f of x dx. And sorry, we are calculating the integral, this is a, this is b, the integral from -infinity to b minus the integral from -infinity to a. We were left with the integral of f from a to b. So here we will have the integral from a to b of f of x dx. So we have obtained very important relationship between integral and probability of a continuous random variable. So probability that our random variable x is between a and b is the integral of f from a to b, which is the same, and I can write this. This is exactly the area under the curve under f over the interval AB, over the interval AB. Okay, and generally the following property is true. The first property is that if x is a continuous random variable, here we need to have continuous random variable with a PDF f of x and CDF capital F of x, then the probability that x is taking a particular value, small x, is 0. And why is this? Because we know that the probability that x is equal to that small x is the value of our CDF at x minus the left-hand side limit of CDF at x. And because for a continuous random variable, this f is continuous, this is continuous, then the left-hand side limit will be exactly equal to f of x, and we will get 0 for this difference. And the second property is that because of this and because of the previous relation we have obtained, the probability that our random variable is between a and b, both including endpoints or not including endpoints, will be this integral, or the area of PDF curve under the PDF curve over the interval AB. So this is very important, and we will calculate probabilities for continuous random variables by just integrating its PDF. And in general, if we want to calculate the probability that x is in some subset of R, then we are integrating over that subset, our PDF. Say if we want to calculate what is the probability that our continuous random variable will be between -1 and 3, or will be larger than, let me write open interval here, say 10 to plus infinity. This is exactly equal to the integral from -1 to 3 of the PDF f dx, and plus the integral from 10 to plus infinity of that PDF. So knowing PDF of a random variable, we can calculate all these type of probabilities. Okay, now we will solve several examples. We'll do several examples. So the first one is the following. Below we have a graph of a PDF of some random variable. So the area under this curve is 1. Which one is larger? The probability that x is 0 or the probability that x is 2? This is 0, this is 2. And the problem is asking which probability is larger. You can pause at this point this video and think about the solution, and then run this video back again. Okay, the point is that these probabilities are both 0. So the height of this is the PDF. So this is f of x, this is the PDF. The value of PDF at this point is not related to this probability. So confusing is that this is higher than that, but important thing is that when calculating the probability, we need to integrate. So we are integrating over this point, this function f, and integral over a point is 0. So this probability is 0, that is 0. So both these probabilities are the same, are equal. The next problem, the next example. So we have a graph of a CDF of some random variable. This is a legitimate CDF. It is increasing. It is right continuous at every point. It tends to 1 at plus infinity, it tends to 0 at minus infinity. So the problem is x continuous. Is the CDF, is the random variable behind the CDF continuous? The answer is no, because if x is continuous, then we need to have that f is continuous. So CDF of any continuous random variable is continuous by itself. So because this function is not continuous, so our f is not a CDF of a continuous random variable. Neither it is a CDF of discrete random variable, because for discrete random variable we need to have step function like this. So this is the random variable behind this CDF is neither discrete nor continuous. You can think about what can be behind this. In fact, this can be, this is a sum of discrete and continuous random variables. The random variable behind this CDF is a sum of discrete and continuous random variables. You can think about that. Okay. The next problem is the following. So we have a graph of some function f. In our next slide, I will show that soon. The first point is, the first problem is to see if it is a PDF of some random variable x. So we need to check that two properties. Let me move forward. So this is the graph of that function. to see if this function, say this, let me call it f of x, our f will be a PDF if and only if it satisfies that two properties. If it is non-negative and the integral over real line is 1. So our function is taking non-negative values. It is 0 here, 0 here, 0 here. So it is 0 starting from 5. And it takes positive values between -1 and 1 and 3 to 5. So it is non-negative. To calculate the integral of this function over real line, we need to calculate the area under this curve, and that area will consist of two rectangle areas. So the first one is this rectangle area, and the second one is this rectangle area. So we can calculate that areas easily. So the height is 0.2 here, the width is 2, so 0.4 here, 2 times 0.2, and here we will have 2 times the width is 2, height is 0.3, this point is 0.3, so the step here 0.1, 0.2, 0.3, this is 0.3, and we will have 0.3 times 2, 0.6 here. So the area will be adding these two will give 1. So the integral of f over the real line, the x is 1. Okay, so we have checked it that this function satisfies the property of PDF. So let's move backward. Just a minute. Yeah. So the next problem is to calculate and show geometrically these probabilities. So probability that x is 0, x is 1, probability that x is less than 1, -1, larger or equal than 0, is between 0 and 2, and is larger than 4. So because we have a continuous random variable with a PDF, so this will be 0 and that will be 0. And that is even, let me show the next slide, the graph, that is even x is discontinuous at 1. Important thing is that we are talking only about PDF, not CDF. So PDF f of x. And the probability that x is taking any particular value, say x is taking the value 1, is 0. Is the integral, I can write that. That is not so nice to write in this way, but this is integral from 1 to 1 of f dx. And this is 0. Okay. The next problem was to calculate this probability that x is less than -1. So this is -1. And to calculate this probability, we need to integrate from -infinity to -1 our PDF f of x dx. So our PDF is 0 up to this point, so its integral will be 0. Okay. The next part of our problem was to calculate the probability that x is larger or equal than 0. This is 0. And we need to calculate what is the probability that our random variable x is taking values from this interval. To calculate this probability, we need to integrate from 0 to +infinity that f dx. And I can calculate that easily and geometrically. This integral will be the area of the PDF graph over this part of real line. So I need to add these areas. So this part area is, the width is 1, height is 0.2, so I will have 0.2 here and 0.6 here. We have calculated the area of this rectangle, so adding them I will get 0.8. So the probability that x will be larger or equal than 0 is 80%, 0.8. Okay. So next was to calculate the probability that x is between 0 and 2. And this is easy to do. This is the probability that this is the integral of PDF over 0, 2. So this is 0, this is 2. And we are calculating this integral as the area under the curve over 0, 2. So we just need to calculate this part's area. And that area will be, of course, we have calculated that width is 1, height is 0.2, 0.2. So 20% chances that x will be between 0 and 2. And the last part of that second point of our problem, for example, was to calculate the probability that x is larger than 4. X is larger than 4 means x is here. X is here in this interval. And this is the integral from 4 to plus infinity of f, and that integral is the area of under the curve of f over this interval 4 to plus infinity. And we just need to calculate the area of this rectangle, the area under the graph of f from 4 to 5. And that is giving width is 1, height is 0.3, so this will be 0.3. Okay, let me erase, sorry. Let me erase this part. Go back to our problem. So part C says find the value of our CDF at 0. Capital F is the CDF of random variable x, and we need to calculate the value of that CDF at 0. And the part D is find analytically the CDF at every point. And the last part is draw the graph of that CDF. So we will do these three. So having the idea is how to find the CDF if we have the PDF graph. So this is our function PDF. This is PDF. Okay. First part was to calculate f of 0. And f of 0 by definition of PDF is, by the definition of a continuous random variable, is the integral from minus infinity to this point 0 of our PDF. So we need to calculate the integral from minus infinity to 0, or which is the same, the area under the graph of PDF, which will give the area of this rectangle, which is 0.2. So CDF value at 0 is 0.2. I'm erasing this, and the other part, important part, was calculate the value of our CDF at every point x. So let's do that gradually. Let me write it here. So f of x. We are calculating the value of f of x at every point x. If x is less or equal than -1. So let me take just one x. This is x. And I want to calculate f of x at that point. F of x at that point is the integral. This is x, sorry. Integral from -infinity to x of PDF. Well, let me write dt here, not confused with this x. Okay, so I need to integrate from -infinity to this point x, my PDF, which is 0, of course, so this will give 0. If I will take another x less or equal than -1, I will get the integral from -infinity to this point, and it is again 0. Even if I will calculate this at the point -1, at -1, I need to integrate from -infinity to -1 my PDF, and that will give again 0. Even if the value of my PDF is 0.2 or anything other. So f will be 0 for x less or equal than -1. Let's consider the case when x is between, so let me erase this part. I'm just erasing this part. Okay. If x is here, so if x is between -1 and 1, I can include this -1, I can exclude that, I can write in, well, let me write it, open interval from this side. Say this is x. So the value of our function f at that x is again the integral from -infinity to x of this function, of this PDF. So I need to integrate this PDF up to this point from -infinity. That is the same as to integrate, is to calculate the area of this rectangle. So I need to calculate the area of this rectangle, and that will be the integral from -infinity to x. This is integral of f dt. To calculate this area, we need to find the height and width and multiply them. So the width is the width of this interval is x minus -1. So width is x minus -1, which will give x plus 1, and times the height, which is 0.2. Okay, and this works for any x between -1 and 1. The next is, let me erase this unnecessary part. So I want to erase this part. Let me a little bit increase the size of my eraser. Okay. Now, let's talk about the case when x is between 1 and 3. So if x is between, let me write it here, x is between 1 and 3. Maybe not including 1 because I have calculated already at the point 1 and 3. Okay, if x is here, if this is my x, I need to integrate from -infinity up to this point my PDF. So I need to calculate the area under the graph of PDF up to this point. But that area is just the area of this rectangle, and that is 0.2 the height times 2. So in this case, my f of x will be 0.4, the area of this rectangle. Okay, this much about the case when x is between 1 and 3. We need to consider this part and then points larger than 5. But before that, I'm erasing this. So if x is from 3 to 5, if I have a point somewhere here, if this is my x, so I need to calculate the area under the graph of PDF, under this function graph, up to this point, and that consists of two parts. So f of x will be, first I need to add this rectangle area, and we know that that rectangle area is 0.4, and I need to add the area of a rectangle up to this line, up to that point. So I need to add the area of this rectangle. And to calculate the area of this rectangle, I need to multiply the height, which is 0.3, with the width, which is the distance between x and 3, and the distance is x minus 3. So 0.3, the height, times, this is point, times x minus 3. Okay. And finally, if x is larger than 5, so I'm not erasing that, if x is now here, then I need to calculate the area under this graph from minus infinity to this point, or which is the same, the integral from minus infinity to x. But that area will give the area of this part plus the area of this rectangle. I'm completing this rectangle, and that will be exactly 1. So f of x will be exactly 1 if x is larger than 5. So if x is here, again, the area up to this point under the curve of PDF is 1, etc. So we have obtained the values of f, our CDF, for all cases. So it is 0 up to the point minus 1. It is 0.2 times x plus 1, between minus 1 and 1. If x is between 1 and 3, f is 0.4. If x is between 3 and 5, it is 0.4 plus 0.3 times x minus 3. And starting from the point 5, f is equal to 1. So let me try to graph that function, the CDF. So, okay, let me just open a whiteboard. So my function is 0 up to the point minus 1, and then up to 1 it is 0.2 times x plus 1. So f of x is, well, maybe I can do the following, right, in this form. F of x is something like this: 0 up to the point minus 1, 0.2 times x plus 1. If x is between minus 1 and 1, and let me go back, 0.4 here, 0.4 plus 0.3 times x minus, I hope this is minus here, that is minus, x minus 3. So 0.4, well, we have x plus 1 here. 0.4 if x is between 1 and 3, and 0.4 plus 0.3 times x minus 3 if x is between 3 and 3 and 5. This is not important where I'm including that point 1 because my capital F will be continuous at the point 1. So the value from this side or that side will be the same. And finally, the value of my function was 1 if x was larger than 5. Now I can graph this function. So the graph of that function will look like the following. This is minus 1, say minus 1, 0 up to this point, then up to the point 1, I will have a linear function, 0.2 times x plus 1. So if x is minus 1, this is 0. If x is plus 1, so I need to take x to be equal to 1 here. I will have 2 times 0.2, 0.4. So this is 0.4. 0.4. At this point, the value is 0.4. At this point, it is 0. And my function is linear, so I need to join by a line these 2 points. Okay. Up to the point 3, I have 0.4. So my CDF is constant up to this point. And then 0.4 plus 0.3 times x minus 3 up to the point 5. So here we have 5. Okay, at 3, the value at 3 is 0.4. I have continuity at that point. If x is 5, I need to put here 5. I will have 2 here, 2 times 0.3, 0.6, and plus 0.4. This will be 1 at this point. So at that point, I will have 1. This is 1. And because I have a linear function here, I need to join this by a linear function, by a line segment. Okay. And starting from that point on, the CDF value will be 1. So this is our CDF. CDF. So it satisfies all properties of our CDF, of course. Nice. So let me erase this. Go back to our slides. Erase this too and move forward. Now, the next problem is asking to see which functions, sorry, I need to change, I want to change that. Which of the following functions will be a PDF of some random variable? Let me sketch the graphs quickly. So f is 0 up to this point, and 1 starting from that point up to infinity. Clearly, the integral of this function or the area under this function will be infinite. If we are integrating from minus infinity to plus infinity, we will have a rectangle of infinite size, infinite area. So this is not a PDF of some random variable. Let me sketch the graph of that. So 0, it is 1 from 1 to 2. So 1 here, this is 1, and 0 up to these points. Let me take another pencil. It is non-negative, G is non-negative, and the area under the graph of G is of course 1 because it is the area of this rectangle. So G is a PDF of some random variable. Now about H. H is our sigmoid function, and sigmoid function graph was, this is 1. We have something like this. And of course, the area under this curve will be infinite from minus infinity to plus infinity. If we will integrate, if we will calculate that area over the whole real line. So this is not a PDF. The next one is M, which is given by this formula. So let me draw the axis. It is 0 if x is from minus infinity to 0. It is 0 if x is larger than 2. This is 2, 0 here. And it is x over 2 linear in this interval 0, 2. So to draw this linear function, I need to calculate the values at the endpoint. So for x0, this is 0. So it is starting from this point. If x is 2, I will have 1. So this is 1. So the graph is a linear function. It is not continuous, but that's okay because we are talking about PDF F. Okay, is this a PDF? It is non-negative, of course. And we need to calculate the area under the graph of F. And the area is just the area of this triangle. And the area of that triangle is this times that, 2 times 1 times 1 over 2. So 1 over 2 times 2 times 1, which is 1. So this is a PDF of some random variable. And later we will learn for which random variable this will be PDF. Okay, and for the last one, k of x is x from minus 1 to square root of 3 and 0 otherwise. Well, you can calculate that the integral of this function, of this PDF, is exactly 1. Just calculate and see. But important thing in this example is that our function is taking negative values for some values of x. Sorry, here 0, here 0, this is square root of 3, this is minus 1. So in this part, our f is taking negative values, but PDF cannot be negative. So this is not a PDF of some random variable. Okay. So we move forward. The next problem is the following. So we are given a function analytically of this form k times x squared plus 1, and x is running between 0 and 1. And the problem is asking for which value of k, constant k, f will be a PDF of some random variable x. If k is positive, then this will be, f will be non-negative function. So we need to take care about the integral of f. So let me write it here. So what we want to have is to have 1 is equal to the integral from, well, let me write over r. This is from minus infinity to plus infinity, f dx. We need to have that this integral is 1 to have a PDF. Okay? So we can calculate, because f is 0 outside of this interval, we can calculate by just integrating from 0 to 1 our function k x squared plus 1. And this is equal to k times the integral of x squared plus 1. Well, I forgot to write the x here. The x. Okay, k times the integral of x squared plus 1. And the integral of x squared plus 1 over 0, 1, I can calculate in the following way. So antiderivative is x cubed over 3 and plus 1. Oh, sorry, plus x, not 1. And substitute it from 0 to 1, which is k times, well, at 0 I will have 0, the value of this function will be 0. So I need to plug the value at 1 minus the value at 0. The value at 1 will be 1 over 3 plus 1, which is k times 4 over 3. So k times 4 over 3 is equal to 1. Now k is equal to, let me write it here, k is equal to 3 over 4. So k here need to be 3 over 4 to have a PDF for some random variable. Okay. Now for the same, for this k and for this random variable x behind this PDF, we want to calculate the probability that x is less than 0.5 or the probability that x is between 0.3 and 0.5. So let me calculate that here. Well, I'm erasing this part. So the probability that our random variable behind this PDF is less than 0.5 is the integral from minus infinity to 0.5 of PDF. Because our PDF is 0 up to the point 0, then it remains to integrate from 0 to 0.5 this function, and k was 3 over 4. 3 over 4 times x squared plus 1 dx. And surely you can calculate this by using your calculus knowledge. I will not calculate this integral. Okay, one common mistake is the following: when people are writing this integral, this probability is the integral from minus infinity to 0.5 of this function, say 3 over 4 x squared plus 1. Well, this is not correct because we need to integrate PDF, and PDF over this interval is given through two different functions. Up to the point 0 it is 0, and from 0 to 1 it is given by this function. So do not write in this way, but write in that way, and then substitute the value of f, small f. Okay, so we have calculated this probability, and calculation of this probability, of course I have a misprint here. I need to have capital X, random variable x. So the probability that x is between 0.3 and 0.5 is just the integral from 0.3 to 0.5 of this function, which is in this case, in this interval, is given by k times 3 over 4 times x squared plus 1 dx. Okay, and I will not calculate this integral again. Okay, so I'm erasing this part, and let's move forward by calculating this conditional probability. So I'm calculating the conditional probability that x will be less than 0.7 given that x is larger than 0.5. By the formula for conditional probability, I need to calculate the following ratio. So probability that x is smaller than 0.7 and x is larger than 0.5 over the probability of this event. So x is larger than 0.5. And now I have x is less than 0.7 and x is larger than 0.5, and I can write that as x is between 0.5 and 0.7, and over the probability that x is larger than 0.5. Now I can calculate this. I'm continuing from this point. So I can calculate that by integration. So I will integrate from 0.5 to 0.7. My f, and f is given by this formula in this interval. So 3 over 4 times x squared plus 1 dx over, because we need to integrate from 0.5 to plus infinity in this case, but starting from point 1, my function small f is 0, then I need to integrate. It is enough to integrate up to the point 1 this function. Hope it is clear. So you can ask, you can write me if you will have questions. Okay, so the value of our conditional probability will be the ratio of these integrals. Nice. So we want to find the value of our CDF, of the CDF of our random variable at the point 0.5 and 1. And calculation of that CDF values is very easy because we need to integrate by definition of a PDF. This is the integral from minus infinity to 0.5 of that PDF. And because our PDF is 0 up to the point 0, we are just integrating from 0 to 0.5, this 3 over 4 x squared plus 1 dx. Okay? And to calculate the value of our CDF at 1, we need to integrate from minus infinity to 1, which is the same from 0 to 1. Now, because I'm integrating from 0 to 1, I can plug this value. I'm writing 3 over 4 x squared plus 1. And this integral was 1, because we have calculated that k from the condition that integral over the real axis, which is the same over the 0, 1 is 1. So this integral is 1, so the value of our CDF at 1 is 1. And if we will calculate, say, f at 1.5, again, we are integrating up to 1.5, which is the same as to integrate up to the point 1, because f is 0 for x is larger than 1, and again, this will be 1. Okay? The next part of this problem is to find analytically the CDF f of x for any x. And later, the other part is to plot the graph of f using R. I will give this R part later, but now I want to calculate analytically this f of x. So I'm opening whiteboard, writing here my PDF. So PDF was 3 over 4 times x squared plus 1, x squared plus 1. If x is between 0 and 1, well, including or not including, that is not important in this case, and 0 otherwise. Okay, so I want to calculate. Let me first sketch the graph of PDF. So this is PDF, this is x. So I have 0 up to point 0. Well, sorry, this is 0. This is 0 point. This is 1. Again 0 starting from point 1. And between 0 and 1 I will have some quadratic function. At the point 0, if x is 0, I will have 3 over 4, so it is starting from some 3 over 4. It will have this kind of shape. You can calculate what is the value at 1. You can plug here x is 1 and calculate this value. This is not important, so this is the graph of our f. Now, our task was to calculate the value of f of x. So let's consider different cases. So if x is less or equal than 0, so we need to integrate f of x is the integral from minus infinity to that x f of t dt. If x is less or equal than 0, if x is somewhere here. If x is somewhere here, then the integral from minus infinity to that point x for this function will be 0, of course, because that f is 0. Now, assume that x is here. So, if x is between 0 and 1, then f of x will be the integral from minus infinity to x f of t dt. So I need to integrate this function PDF up to this point. Because our function is 0 up to 0, then I need to just integrate from 0 to x this function. And that function is 3 over 4. 3 over 4. Well, I'm writing here with t, not to confuse with that x. Later I will plug that x dt. And this is equal to 3 over 4 times the antiderivative is t cubed over 3 plus t, and I need to plug x minus the value at 0. The value at 0 of antiderivative will be 0. You can check that, and I will get x cubed over 3 plus x. So this works up to the point 1. And what about if x is larger than 1? Then f of x will be again the integral from minus infinity to x f dt. And in this case, if x is somewhere here, then I need to integrate up to this point. I just need to calculate the area or integral over 0, 1. So integral from 0 to 1, this is 0, of 3 over 4 t squared plus 1 dt, which is 1, because we have calculated that constant k by that property, that in the integral of our PDF over real line, or this area, which is the same, this area is 1. The last part of this problem was to graph this small f and capital F in R. I will do that in a separate video. Okay, so sorry, let's move forward. The next example is 22.7, seventh example in this lecture. Now we consider a random variable, given by this PDF. So this is a PDF. Sorry. This point is 0, this point is 0.01, this point is 0.01, and this is 1, this is 1.9, so, sorry, not 1.9, but 2.9, so I'm giving the discontinuity points of f. You can check that the integral of this function will be 1. It is easy to check. Are the chances that x is close to 0 high? So one important thing is that you can see that this PDF is taking the value 5. So this PDF is larger than 1 at some points. So this, in fact, this interval is very small. So on a very small set, we can have very large values for our PDF. This is the answer for example for one of the previous questions, whether PDF needs to be between 0 and 1 or not. So it can be outside of that interval 0.1. It can take large values. Okay, so the probability that x is close to 0, say x is from minus 0.1 to 0.1. So how do I am calculating this probability? To calculate this probability, I need to integrate from minus 0.1 to 0.1 our PDF, which is given through this graph, dx. And this integral will be the area of this very small rectangle, and the area of that rectangle will be, sorry, I do not want to mark that up to the end, well, this rectangle, and the area of that rectangle will be the height, which is 5 times the width, and the width is 0.01, so 0.05. So we have just 5% of chances that x is between minus 0.1 and 0.1. So there are very low chances that x is close to 0, even if the values of our PDF are very high, close to 0. So most of the concentration, most of the values of our PDF, of our random variable, x with this PDF will be between 1 and 2.9 will be here. So how do we are reading information about random variable from its PDF? So what is the probability that x will be between 3.1 and 3.9, say. So this is 3.1, sorry, this is 3.9, and we want to see what is the probability that x is here. So the probability that x is here can be calculated by just integrating the PDF from 3.1 to 3.9, and because our PDF is 0, we will have 0. So no chances are 0 that x will be here, and chances are 0 that x will be here, and the chances are 0 that x will be less than 0, x will be here. Very small chances that x will be between 0 and 0.01, this is 0.01 point, and chances are high that x will be between 1 and 2.9, this is 2.9. So another example about reading information about random variable from the graph of PDF. So what a PDF graph is saying about that random variable? In fact, it is giving everything, almost everything we can know about random variables. We can calculate all necessary probabilities for that random variable by using the graph of PDF, well, by using that PDF. So this is the PDF of some random variable x, and we want to describe that random variable x. First, let's check that f is a legitimate PDF. So it is 0 outside of 0, 2 union with 4, 6, and the array under this graph will be the area of this triangle plus the area of that triangle. These two triangles are of equal area, and the area of this triangle will be the base length. So 2 times 1 over 2, sorry, times base length 2, and the height, which is, well, this is 0.4, this is 0.5, 0.2, 3, 4, 5, 0.5, 0.5. So the area of this triangle will be 0.5, so 0.5 area here, 0.5 area here, and we will have area is equal to 1 under that curve. Okay, we are calculating these areas. So this area sum will be 1. Okay, I'm erasing. So this is a graph of some PDF. And let's talk about the render variable behind that PDF. Okay, so what is the probability that x is taking values between minus infinity and 0? So minus infinity and 0. What is the probability that x is here? We need to integrate our PDF, this function, from minus infinity to 0, and we will obtain 0. So no chances that x is here. Also, no chances that x is here. So the probability that x is between 2 and 4 is again 0, because we need to integrate 0 from 2 to 4. And no chances that x is larger than 6, because again we will have that probability 0. So possible values of x are between 0 and 2 or between 4 and 6. And what is the probability that x is between 0 and 2? The probability that x is between 0 and 2 is just the area under the graph of PDF over that 0, 2 interval. So I need to integrate this function, which is the same. I need to calculate this area, triangle area, which is 0.5 as we have calculated. So half of the time the values of x will be between 0 and 2. And half of the times, so 50% of chances that x is between 4 and 6. So we can give this kind of probability. So we can calculate what is the probability that x is between 4 and 4.5, or 4.5 and 5.5, etc. We can calculate this kind of probabilities. We can get these all probabilities by using the PDF graph. Let's move forward. Another important example. So this is somehow theoretical example. So given the graph of PDF of a random variable x, construct the graph of CDF. So CDF was the integral of PDF. So this is the same as to find the graph of integral function having the integrand. And the second part is the inverse problem. We have the graph of CDF and we want to construct the graph of PDF. So we have the graph of capital F. We want to calculate, we want to draw the graph of its derivative, PDF. Let me give the idea. So the first problem was about obtaining the graph of CDF from PDF graph. So here I want to draw the PDF graph. Say we have something like this. So 0 up to some point, then this kind of bump, then 0 up to another point, then another bump, and 0. Say we have this kind of graph for PDF up to plus infinity. Assume that the area under this graph, that is the area of these two small regions, is 1. So this is a legitimate PDF graph. And now we want to obtain the graph of CDF. So I will draw that CDF graph here. So this will be CDF below. Okay. So to calculate, let me check this point. This is the same point on the axis. This is X. This is again the same X. Okay. To calculate the value of our CDF at this point, I'm looking here, the same point, and I'm integrating this PDF, this function, up to this point, or which is the same, I'm calculating the area up to this point under the graph of PDF. So because f is 0 up to this point, then the value of CDF at this point will be 0. So what is the value of our CDF at this point? Again, I need to integrate this function up to that point, and again I will get 0. So basically our CDF will be 0 up to this point. Say if I want to calculate the value of our CDF at this point, I'm looking the same point here, and I'm fixing the same point here, and I'm integrating up to this point my PDF. So area under the graph, it is 0. Okay, so if I want to calculate the value of my CDF at this point, so this is the same at that point. So now I need to calculate, what I need to do is I need to calculate, let me change the color, say red. I need to calculate the area under the PDF curve up to this point, which is the same. I need to calculate this part area. Because the total area is 1, this part area will be small number, so I will have some small value here, but non-zero number. If I'm moving this way, I want to calculate the value of my CDF at this point, which is the same. I'm taking the same value here. I need to calculate the area up to this point. So up to this point. So area left to that under the curve of PDF. So it will be a little bit higher than this value. It will be somewhere here. Okay. Now let me take this maximum point, say this is that maximum point, and think mathematically. So this is small f graph. Let me take that blue colored pencil. Okay, this is f, this is capital F, and we know that f prime, the derivative of capital F is small f. So I know the graph of small f. It is non-negative, of course. In this interval, it is strictly positive. So this is strictly increasing in that region. So if I will mark this point. So between these two numbers, the graph of capital F CDF sorry, will be strictly increasing. What else I can say about that capital F? Let me calculate the second derivative of my CDF, capital F. That will be the first derivative of f. And in this region, up to this maximum point, up to this point, small f is increasing. So small f is increasing means that the derivative is larger than 0 in this region, So that means that double derivative of CDF is positive. And if double derivative is positive, then we will have a convex function. So I want to draw that graph up to this point, up to that maximum point for PDF. We will have this kind of graph. Then after this point, f is decreasing. Small f is decreasing. If small f is decreasing, then in that case, this will be less than 0. So I'm talking about the points here. So if this is less than 0, then f double prime, the second derivative of CDF, will be less than 0. So I will have increasing but concave function. So in this part, I will have a concave. So this point, which was the maximum point for our PDF, will be the inflection point for our CDF. Okay, let's move forward. What will happen if I will calculate the value of my CDF at this point? So I need to integrate from minus infinity to this, but this is the same as to integrate up to this point. So at this point and at that point and even at that point, I will get the same value. If I'm integrating up to this point, I will get the same value. If I am integrating up to that, I will get the same value. So up to this point, I will have a constant function. And that constant will be the area of this part. Okay. If we will continue studying in the same way, up to this point, our small f will be increasing. So our f is increasing up to that point and then decreasing. So my CDF will be convex up to that point. So this is that point. Then it will be concave. And starting from this point on, the values of my CDF will be the same, because the integral up to this point is the same as the integral of this small f up to that point, because that small f is 0 starting from this point on. So I will have a constant, and of course the integral up to this point will be 1, because it will be the sum of these areas. So this is 1. So we have obtained the graph of capital F CDF from the graph of PDF. Okay. So let's solve the inverse problem. The inverse problem is we have the graph of CDF. Now we are given the graph of CDF. Sorry, think as a straight line. So this is the CDF graph, and I want to obtain here below the graph of PDF. So this is, oh, sorry, let me write somewhere here. This needs to be the graph of PDF. Okay, let me take this kind of graph. So 0 up to some point, then something like this, then constant, then linear, say, then 1, because I need to have, this is 1. My CDF needs to tend to 1. I'm assuming that starting from this point on, it is exactly equal to 1, and it is linear in this part. It is constant in this part, some function, continuous function, increasing continuous function here, and 0 up to this point. Now, this is the graph of f of x, the CDF, and we need to calculate, and we need to draw the graph of PDF. And we know that f prime of x is small f of x. This is the PDF. And this is the CDF. Okay, so we need to draw the graph of the derivative of this function. Well, if I will take the same point, here, the derivative of this function at this point will be 0. The derivative of this function at this point will be 0. So here I need to draw the values of the derivative of this function. So up to this point, I will get 0. So this is 0. Also, if I will take these 2 points, the same points here, capital F, CDF is constant here. And here I need to draw the derivative values. Because the derivative of a constant is 0, here again I will have 0. Starting from this point on, the same point here, my function is 1, my f of x is 1, so f is constant and derivative of that constant will be 0 again. So the graph of PDF will be 0 in these intervals. Now what about this interval? Because it is linear here, then the derivative of a linear function will be a constant, and that constant will be equal to the slope of this line. So and the slope is, let me just show in other color, say the slope is something like this. The tangent of this angle. So this is close to 45 degrees. The tangent is 1. Say, let us think that it is equal to 1. So I will have a constant 1 here. Say this is 1. Okay. So we have this part graph, and it remains to talk about this part. So this is the inflection point. Say this is the inflection point of our CDF. So up to this point, our CDF is convex. If CDF is convex, then in that region, I will have the double derivative is positive, well, non-negative. This means that because the double derivative of f will be the first derivative of small f, that means in the same region, in the same interval, I will have this is, well, these two are equal. The first derivative of PDF is non-negative. And if the first derivative is non-negative, then I will have increasing function up to this inflection point of CDF. So say it is increasing in this way. Okay, similarly, because we have concave function here, and the second derivative is non-positive, I will have this is non-positive, so f prime is non-positive means I will have decreasing function. So this is the graph. Say, what is the value at this point? How to read the value at this point? What is the value? Maybe I have this kind of graph or this kind of graph, increasing then decreasing. To find the value at this point, I'm looking at that point here. And I need to calculate the slope of the tangent line to the graph of CDF at that point. So the graph, the CDF tangent at this point will have some slope, and that slope value will be the value of our PDF at this point. I hope this was clear. So I'm erasing everything. Moving forward. The next example is the following. So let x be some real-life example of a random variable. Let x be the random variable showing the closing price of some stock today in thousands of dollars. Then can this function be the graph of the PDF of random variable x? We assume that the array under the graph is 1, so this is a PDF. Can this represent this random variable? Can this be the PDF of that random variable? Well, this is 10. If x is 10, capital X is 10, that means that the closing price will be $10,000. X is 20, that means the closing price will be $20,000. So we can calculate what is the probability that X will be between $10,000 and $20,000 by just calculating the area of this part. That will be close to 0.4 because this graph is symmetric. The total area is 1, this part's area is 1, and we are calculating just part of that area. Okay, so 40% probability that X will be between $10,000 and $20,000. That closing price will be between $10,000 and $20,000. But the problem was, can this function be the PDF of X? In fact, no. Why no? Because you can look at this part and see that the probability that X is less than 0 X is less than 0 is this area, and that area is not 0. So we have a positive probability that the price will be less than 0, but the price cannot be less than 0. So this cannot be a PDF of our random variable representing stock price, positive random variable. So if we have the general idea, let me erase this and give the general idea. If we want to have the PDF of this random variable X, which is non-negative, which takes only non-negative values, then we need to have something like this. It needs to be, this is PDF, sorry, let me specify that this is PDF. It needs to be 0 for negative values of X, small x, and have this kind of shape. Okay, so high probability that my values will be here. Well, I need to have this kind of thing, because the probability that the values of X will be very large will be very small. Okay, we will have this kind of the shape of graph for PDF for our random variable X, which is taking non-negative values. Okay, so we are moving forward, and the next problem is of the previous problem sort. So a sort of the previous problem. So assume X is a random variable representing the weight in kilograms of a randomly chosen person at AUA. Can this function given by this graph be the PDF of that random variable X? So X is a random variable because we are calculating the weight of a randomly chosen person. X is continuous random variable. So can this function be the PDF? Our function is 0 up to the point 0, so it is nice. So this shows that X cannot take negative values, and because X is a weight, X indeed cannot take negative values. But what about the shape of this graph? Assume that the area is again 1, so it can be a PDF. But can it be a PDF of this random variable X? In fact, again, no, because this shows that the probability that this graph shows that the probability that the weight of a random person to be larger than 20 is the area under that graph, and it is very small. But of course, the probability that, and hopefully that the probability that weight of a randomly chosen person will be larger than 20 is very high in reality. So this is not a nice graph for that random variable. Okay. So you can think about the shape of the graph of that random variable. Later, during the statistics course, you will obtain that shape by considering different samples by considering different persons with different weights, and using that data you will construct the approximation of this PDF. Okay, so let's summarize what we have learned for discrete and continuous random variables. So we have learned that we can describe any random variable by its CDF. This works for any random variable, discrete, continuous, and even for singular ones or mixture ones. We will not talk about these two. We are talking just about discrete, continuous random variables. We can describe them if we have the CDF. We can calculate all probabilities by using CDFs. Next, if X is a discrete random variable, then we can describe that random variable by its PMF, probability mass function. But if X is a continuous random variable, then we can describe it by probability density function, and there is an error misprint here. I will correct that, sorry. This needs to be, this copy paste error, this needs to be PDF, probability density function. Sorry. And if we have either of these, if we have PDF, PMF, or CDF, then we can calculate probabilities concerning that random variable. Okay? How to calculate probabilities by using CDF. So the definition of CDF was the value of CDF at point X is the probability that random variable will take the values less or equal than X. And we can calculate this probability of taking the particular value A by f of A minus the left-hand side limit of CDF at A. And this probability is just the difference between f of B and f of A. Now I'm giving both discrete and continuous cases calculation of probabilities or relationship between CDFs and PDF, PMF in a table form. So for discrete random variable, the probability that X is taking the value xk is the difference between the value of CDF at xk and the left-hand side limit of CDF at xk. So this difference is giving this probability. And for PDF, the analog of this for continuous case is that our PDF, this is PMF is equal to the difference of CDF, and here PDF is the derivative of the CDF. The value of the probability that X is equal to that particular value xk is pk, and if here I will plug a value which is not a point, which is not a value of our random variable X, then this probability will give 0. But for continuous random variables, this probability is always 0. So in the discrete case, if we are taking the value of our random variable X, then we are getting the probability that will take the value xk. Okay, we have this property, the sum of all possible probabilities in the PMF. In the second row of our PMF is 1, and the analog of this is that the integral of PDF over the real line is 1. The CDF can be expressed in terms of probabilities in this way for a discrete random variable, and for a continuous random variable we are integrating from minus infinity to x the PDF. So here we are adding the PMF values up to the point x. Here we are adding, in the sense of integration, the values of our PDF. So there are some similarities between continuous and discrete cases. Okay, and to calculate the probability that X is between A and B, we need to add the values of PMF for all values xk that are between a and b, and to calculate for a continuous random variable the probability that x is between a and b, we need to integrate the PDF between a and b. And last thing, a warning about common mistake people are doing. If x is a random variable and a is a number, then x is not an event, so we cannot calculate the probability of x. So writing probability of x is incorrect. Writing probability of some number, probability of 3 is incorrect. But instead, these sets are events, so we can talk about the probability that x is taking the value a, or probability that x is taking value less than a, or larger or equal than a, etc. So these probabilities are correct, but these are not correct. We cannot calculate the probability of x. And one example I was giving that in my previous lectures too. Another example is, say x is the number of emails I will get today, and this is a random variable, this is a discrete random variable. Then if I will write px, this is the same as asking what is the probability of the number of emails. Probability of number of emails. This is nonsense, this is meaningless, but of course I can talk about what is the probability that the number of emails will be 0. I will not get any email today. And what is the probability that I will get more than 10 emails today, etc. So these probabilities have clear meanings. So this much for today, this much for general theory of continuous random variables, and soon we will talk, next time we will talk about concrete examples of discrete random variables, and then about concrete examples of continuous random variables. So thank you, bye.